I want to talk about parallelism in field programmable gate arrays using Hume. I should explain that I'm responsible for the first half of this work, and my friend Jocelyn is responsible for the second half of this work. So when people who know what they're talking about, like Mary, want to ask difficult questions about the second half, I'm probably the wrong person to ask. Okay? Okay. Field programmable gate arrays offer us an alternative to CPUs for implementing software directly in hardware. These really come back to what Paul was talking about this morning, the idea in ENIAC of directly configuring the components of a computer to reflect the computation that you want to perform, rather than implementing the generalized FX execution cycle. Essentially, it's a complete customization of the hardware for a specific program. So to program an FPGA, you've got to configure the logic elements, and you've also got to configure the communication between the logic elements. So FPGAs give you immense amounts of very fine-grained parallelism. And the density of processing elements in FPGAs is getting bigger and bigger, and the price is reducing more and more. But typically, they're programmed using hardware description languages like VHDL or Verilog. This offers a relatively high-level solution compared with working at a gate-level configuration in a register transfer language, but you still need a tool chain to get you down to the register transfer language. And at the same time, you have to think about really quite low-level considerations compared to normal languages that we work with. It exposes all the local hardware concerns like clocks and buffering and so on. So you've got this very sort of unfortunate mix, which is traditional in system programming languages, of the balance between high-level constructs and exposing very low-level features, as anyone who's programmed in BCPL will recall. Okay, so Hume was a language developed by myself and my mate Kevin at St Andrews over the last 10 or 12 years. We met Jocelyn at Clermont-Ferrand in the EU Bounded project. Essentially, it's a formally motivated language driven very strongly by foundational ideas about computing. And the idea is to build systems which are resource aware. We want to have cost models that will accurately predict the behavior of Hume programs and enable us both to give assurances that things will happen when they're supposed to happen and to drive optimization of implementation. So Hume is really old-fashioned stuff. Essentially, it's concurrent finite state machines. And inside each box, the box is a finite state machine. You've got transitions. The transitions will be familiar to this audience. They are essentially polymorphic functional language. You've got rich pattern matching on the left-hand side of the transition and arbitrary recursive functions on the right-hand side of the transition. So outside the box, it looks like a finite state automata. Inside the box, it looks like some peculiar child of ML and Haskell, reflecting Kevin and Y's profound ideological differences about how to design functional languages. Kevin is a member of the Haskell school of thought. I'm a member of the, I suppose, ML or early Sassel school of thought, which are profoundly different. I think Hume actually is not about compromise. Okay, now the nice thing about Hume, for many reasons, in particular cost modelling, is a very strong separation between coordination, that's the behaviour between the boxes, and the expression level, if you like, the computation that takes place inside the boxes. This means that you can reason very elegantly about these two levels quite independently of each other, and in principle, you could populate boxes with another language, with an arbitrary language, because coordination is semantically quite distinct from the language used for defining transitions. Very strong formal foundations. We've published static and dynamic semantics and a type system. There are also very robust resource predictors for quite specific low-level microcontrollers. Two ways of doing this, either via an abstract machine interpreter or through compilation to seek. I should explain briefly that there is a tool chain centered on the Hume abstract machine, and as long as everything goes through the abstract machine, then the resource analyses developed in Munich and St Andrews can be applied, provided you have parameterizable models of the hardware that you're running. Okay? So the Hume abstract machine sits right in the middle of our entitled chain. So here is a rather peculiar example. This is one of those things for tormenting cats with.
Maybe one has picked it up.
Maybe there are no cats. Okay. Excellent, a lightsaber. So 3 buttons, will I get the right one first time? Thanks, Paul. Okay. So, this box is generating successive integers. There's a feedback loop here between n prime and n. Every time it sticks out the next integer down the R wire and increments the input n and passes it back round. Okay? This box here is doing squaring by repeated addition. Okay, so to square a number, what you do is you add it to itself that number times. So here you've got the sum, that's where the squares are accumulating. Here you've got the count, that's where you're decrementing. And here you have got the value that is going to come out of the end, I think. So looking at the matching, that star means ignore the input. S will bind to the current sum. 0 is a match, it gives you a condition. V is not used here, I'll put it in because I'm going to show you later the bindings that we generate in the FPGA code. In this stage, C is not 0, so we add V to S, and then we take 1 away from C. So C on this wire here is declining until it hits 0, in which case this rule will fire and we'll get the output. Here, where we do want a value on I, and these 2 rules we're ignoring I, here we do have a value on I that comes in from the previous box. We then reset S to 0, the count to that value on I, and the V, the value we're going to add repeatedly to I as well. So we're going round and round and round, adding I to itself, I times, until we get to 0, and then we squirt out the result at the bottom. We're outputting to standard output, we're wiring the ink box. So wiring is my position, that says that n is wired to n prime, and it's initially 0, and R, the output, is wired to square I, square's input is wired to ink.r, S is wired to S prime, C is wired to C prime, and V is wired to V prime. Okay? Paul again may recognise this from Caliban, very similar to Caliban, and like Caliban, not uninfluenced by Occam wiring. I think that'd be a fair thing to say. Yeah.
Can you quickly explain why the first and the third of a clause is, why is the I? What's the difference between the first and the third? The star and the I.
Star means ignore.
Okay.
So star just says, I don't care if there's an input or not. I says there has to be an input and I'm going to bind.
So there's a difference in semantics whether it's an input or not.
Yeah. So if we didn't have these 2 rules and there wasn't an input, then it would just block forever. The star enables us to ignore an input, so it's a way of giving us non-deterministic behaviour in boxes. Okay? I can't really sort of tell you about the semantics here, but it is trust me, I'm a doctor, well defined. So typically we want to generate 0, 1, 2, 3 on the input, we want to output 0, 1, 4, 9. Okay? So we are going to have 3, let's say, coming from the ink box into the square box. And then round and round we go. We've got 0, 3, 3, 3, 2, 3, 6, 1, 3, 9, 0, 3, and then 9 comes out on the output. Okay, now I could have written this using a recursive function, and I could then have applied box calculus to refine it into a pure box. So I've done it this way because I want to focus on the coordination, not on the functional language inside. Okay. In a previous project called ILA, we looked at putting Hume onto field programmable arrays, but we used a soft core approach. We looked in particular at putting, first of all, the ham bytecode interpreter onto the FPGA. We also looked at compiling the ham code to native code on a core for an industry standard CPU on the FPGA, and we also looked at compiling Hume programs directly to native code. Okay, the good thing was it used the classical Hume compilation path, which meant in principle we could use the cost modelling to predict behaviour on the FPGA. The bad thing is the scalability is absolutely dreadful. We can only get 10 of the ham cores or 10 of the soft CPU on the FPGA. It's very, very coarse grained, so it's really wasting the capability of the FPGA, and it's really quite slow. You end up with a limited clock frequency. So our new approach is to go from Hume, not going through the Hume abstract machine. I don't think that's the problem. I'll talk about that later on. Through compilation to VHDL, and then go through a standard synthesis toolchain in order to get a gate level description on the FPGA. Okay? Now, I started out at the beginning telling you that Hume is based on finite state machines. And we all know that FPGAs really like finite state machines. Okay? So this gives us a very different approach to that, for example, of the Lava group, who are going from pure functions. We would use, in contrast, something like our box calculus, which recently was published in the Central European Functional Programming Workshop, to go from a pure functional program right down to a state machine in Hume. Box calculus gives you a way of going from pure functions inside the box into iterative functions with very, very, very primitive box internals. Okay, so we have a formal methodology which I think is fully in keeping with the spirit of this august workshop where the word function features prominently. Okay, Hume is Turing complete. We're working with the Hume subset I've been experimenting with called mini-Hume. I can also generate OpenMP and MPI for mini-Hume to place individual boxes on separate cores or separate processors, so it seemed interesting to try and use this as well for FPGAs. You've got fixed size integers, there's no functions. As I say, it's not a problem because we have a formal way of refining functions into boxes, and we're limiting expressions to arithmetic and logical operations. Okay, so here's mini-Hume. I won't bore you by reading the syntax. It actually has got quite a lot of Hume. It's got box definitions with the input wires, the output wires, and the matches. It's got the full wire definitions. The matches give you arbitrary matches with patterns to expressions. The patterns include integers, variables, and the don't care variable. Expressions are much simpler. Integer variable, bracket expressions, or operator expressions, operators for arithmetic. And then you've got streams which enable you to connect to an outside environment. So that's the way of getting you onto memory, and maybe onto some sort of port, as well as onto a file, or indeed an HTTP connection, should you wish. And we've got very simple types. Okay. 3 steps to compiling Hume to VHDL. First of all, you generate a network, then you do box translation, then you transcribe to VHDL. I'm going to use a very small example to show this. Okay, so for network generation, typically in the Hume program, you've got the box-to-box transition on the wire. We have to introduce a new construct to make a wire explicit as a single-stage buffer. Okay, so we've got handshaking, writing from the first box, reading on the second box. You can check whether the buffer is full or not on the first box, empty or not on the second box, and you've got an input into the buffer and an output to the second box. Okay, so we take a Hume box, and surprise, surprise, we go straight into a finite state machine representation. The translation is guided directly by the Hume dynamic semantics, but the important difference is that all transitions will occur simultaneously and are synchronous to the global clock. Okay, so that's unlike what you'd expect in a multi-core or a multi-processor implementation, where we use a BSP-like superstep to coordinate input and output. Okay, so basic Hume scheduling, this is the thing that's appeared in pretty well every Hume paper we've ever produced. It says, forever, for each box in a ready state, find a rule which matches the inputs, bind the pattern variables, evaluate the expressions to produce the outputs, but don't assert the outputs, and then go into the block state. So that's like BSP, the fourth superstep. And then we say for every box in the block state, consume the matched inputs, assert the outputs, put the box back in the ready state. So here, every box does its internal stuff and potentially produces outputs. Here, the inputs are finally consumed and the outputs are asserted. So, you were asking about the ignore variable. In a case where you don't have ignore variables and you've got a real variable and there's no input available, then the box wouldn't be ready because the box feeding it would have blocked output. And so box feeding it wouldn't be able to do anything until that box was in a ready state, consume the output, and then the generating box would run generating. So the synchronous reformulation is to do exactly the same thing, but to do it on every clock cycle and to truly do everything in parallel. Okay? Now notice that we are not separating out the internal box stage from the superset stage. We're actually doing these in parallel. Okay? Okay, so to get from a box to a finite state machine is kind of obvious. The box has got pattern 1, expression 1, pattern I, expression I, pattern N, expression N. We say here, if the condition on wire I is ready, then we do the action for wire I. That's a read action. And similarly, in the other way, if the condition for writing on wire I is ready, then we do the write action on wire I. So we've gone directly from pattern expression to conditional input, action on input, condition on output, action on output. So if we look at the square box, you see that quite straightforwardly. So here, we are ignoring input 1, we're saying input 2s is available, input 3 is available, we can batch input 3 to 0, and then we've got to bind input 2 to s and input 4 to v. And then on the output side, if output wire 1 is available, we write s on wire 1. Similarly, for the second match, we're ignoring input 1. If 2, 3, and 4 are available, then we bind 2 to s, we bind 3 to c, and we bind 4 to v. And then for the right-hand side, if outputs 2, 3, and 4 are available, we write s plus 2 on 2, c minus 1 on 3, and v on 4. Okay, so there's a very, very natural one-to-one transcription from the patterns and expressions in the box match to equivalent much lower level finite state realization. Okay, then the program is a VHDL component. An I/O stream is a dedicated VHDL process, certainly for our simulation. And box finite state machines go to VHDL processors. VHDL process, well, firing and writing conditions, you get full of empty signals. Generation of read and write signals requires one extra state per rule. Well, that's really not a big deal in terms of the overhead. Okay, so here's a box that x becomes x plus 1. Here we expose the buffer. And at the bottom you can see the initial finite state machine, and here we've got the clocked condition, input full, set x to the input data, for the first transition, output empty, set the output to x plus 1 for the condition, and then on the clock cycle, that's the additional cycle, come back down to the ready state again.
Enough Hume.
Oh, we never have enough Hume. Never ever. Too much Haskell. Probably too much dependent types as well, but there you go. Okay, so here's an ink box again, that's the one we looked at just now with the feedback loop. Okay, this is the, I think, VHDL that gets generated, I won't bother talking you through it. We've got very preliminary experimental results using the Altera Quertus trademark toolchain. I/O streams to and from files, simulation plus synthesis. We're going to show a simple Perceptron example. Perceptron's a really ancient piece of AI, sort of prefigures neural networks, essentially how to compute a binary function using a training set with a two-phase algorithm. We've got feed forward, where you compute the output with the current weights, and back propagation, where you update the weights after comparing the computed and expected output. So it's really sort of classic application of finite state automata, pleasingly late 60s, early 70s. It converges in a finite number of steps if f is linearly separable. Okay, so here's the Perceptron. Just want to show you some exciting boxes. I box, 3 N boxes, an S box, a V box, and the output box. Okay, let's look at what these things are doing. I is the input box, N are 3 neurons. We could expand that arbitrarily. S is doing the sum of products, and then that's doing the correction and feeding back for the next stage. Okay? And then the iteration control is that other box. Okay, there's the code in Hume, not very exciting. Essentially, large numbers of pattern matches and activities corresponding to perceptual behaviour. Okay, it's 80 lines of Hume, it's 500 lines of VHDL when you do the compilation. Isn't it bad, I suppose, it's about a 6 point something to 1 ratio. Okay, here's the simulation results. I won't even begin to explain it to you, probably because I can't. So I can explain in slightly more detail. It's the synthesis result. This is the overall network. So the 4 big boxes, big final 1, 2, 3, 4, are the N boxes of the O box. The medium-sized boxes are the S and the B boxes. And then the S box, we have got 2 adders and a comparator. There's these big circular things here. And then we've got the rectangle is the finite state machine control. Okay? So, we've got a simple formalised model for compiling Hume to VHDL. There is a very simple translation semantics in the paper in the proceedings. I think this offers really, really good opportunities for exploiting massive fine-grained parallelism from FPGAs. They can get really quite good silicon utilisation of performance compared to the soft core performance. I mean, it's massively faster than the soft core and has much more opportunity for better use of the silicon area. Hume is, well, I suppose it's yet another very high-level language. Okay, so in the future, I want to enrich the expression layers for Hume. I've now got recursive functions and tuples and vectors working, so we're hoping that we can build our toolchain to VHDL to actually do some slightly more convincing large-scale programs on the FPGA. I want to integrate and extend the macro language for specifying large and complex networks. The macro language is really horrible. Paul used recursive functions to wind up Caliban. We use things that look like for loops, but we think Paul's approach is better, and we will be stealing that at the next opportunity, Paul. Yeah, of course, you should use higher order functions for wiring boxes together. Also, I want to use the Hume box calculus to automatically derive box level formulations from the function level specifications. And we want to use the resource analysis for Hume to try and predict time and space behaviour on the FPGA to try and reorganise the boxes to get even more optimal mappings onto the silicon. Okay, well, thank you very much.
Questions?
So you've shown us some feedback cycles, cyclic graphs here, and in the case where the box has quite a deep combination of a deep expression, for example, a floating point add or something like that, you're going to want to pipeline that. That means that when you build a cyclic graph, actually it's going to come back several cycles later. Do you stall there, or do you do some kind of, what I'm really getting at is whether you're able to do retiming at C-slope?
At this stage we can't. That's certainly something that we need to look at. Really, we were focusing on getting this very primitive toolchain to work. You've raised a fair point, and it's certainly something that we need to look at.
It strikes at the heart of quite what level your language is really at. You can specify computations at a level that exposes retime to the compiler, or you can have a do what I say level that says, no, this is retime.
Okay, so we could use the box calculus to pull out further layers of subboxing in box pipeline. There's an extension that our PhD student Goodman put together called hierarchical Hume, where you can compose and encapsulate boxes, and you can then reason about a box within an encapsulated box and guarantee that changes at that level won't affect the timing behaviour of the wider system. So that might well be the way to go to accomplish what you're suggesting. But yeah, we do need to do that, and no, we don't have to do it yet.
Hi, I've got a two-part question. So I was going to ask about the metaprogramming story, and it's because, to my knowledge, so BlueSpec certainly, and I think Lava also depend pretty heavily on metaprogramming via embedding in a host language or having a custom metaprogramming language. So is the plan for Hume to just continue to stay in macro language, or to embed in something else?
Yes, we want to stay purely within Hume, as far as we can. But there's 12 years of work. There's a really well-developed toolchain that generates very decent code for arbitrary single and multiprocessing platforms. So we don't want to go beyond that.
Oh, I wasn't talking about replacing that, but just the macro language on the front for.
Yeah, but, you know, we would just put in higher order constructs for generating the wiring to replace the current iterative constructs. I think that's not controversial.
Right, that's
So what is controversial probably is we need to do higher order macro expansion, because that would be done at compile time rather than at runtime. So we probably need an interpreter available to do that. But we haven't, so that should be feasible.
The second part of the question is just for those of us who aren't intimately familiar with this area, could we draw a bit of a distinction between what Hume provides in this area versus Lava?
Yeah, sure. Lava essentially is a pure functional language, okay? You could argue that Hume is not a pure functional language. Inside a box, it's pure function. Boxes do not retain state on each iteration. That's very nice. It means we don't need to have any garbage collection. If you run out of memory, you run out of memory. If you haven't run out of memory, then you can just reclaim it all on the next box cycle. It means also that you don't need an operating system present. We can generate just straight native code to run on the board, provided it's got a USB connection or something. Okay? The coordination level is stateful because wires, as you've seen, retain information on iterations. So you could, and something that we've been talking to the Lava people about is put Lava inside Hume boxes, or use the Lava language environment inside a box, and then use the Hume calculus to refine from pure functional Lava outwards into a more stately and stateful approach.
But how about Hume boxes versus BlueSpec's guarding atomic actions?
Yeah,
what's the relationship?
I don't think there's any clear relationship at all.
Okay.
Quick question about related to Paul's question. Pipelining is one aspect that plays a role in getting good performance on FPGA or actually any architecture. The other part is communication complexity. So while in the box calculus it's equal, we can account for the pipelining. I was wondering about the communication complexity in the sense of, you know, if you have long wires in the eventual layout, 2 or 3 dimensional layout, is there any way of accounting for that?
Well, okay, you can do some very simple things. You can turn multiple wires into tuples. So you could use that essentially to chunk very small communications into larger communications, where you've done data flow analysis on the box communication to establish that in practice a group of wires are always active at the same time. It may be that a designer is exposing independent wires with very, very small entities on them, where there's a direct equivalent, where you want to say bunching the data together to give you a more efficient communication path. That would be one thing you can look at doing. Another thing you can look at doing is, as well as being able to pull boxes apart, you can push boxes together. So you could reduce the communication by doing more work inside a box horizontally instead of between boxes vertically.
But these boxes they're connected by an arbitrary graph, right?
Yes.
That when you lay it out might have differences in terms of how far away the components are once they're laid out.
Sure, but as I'm saying, if you compose boxes together, then you can make the distance between boxes vanish.
So there's like a layout algorithm you're thinking of, just like VHDL has to solve that problem too. So
no, for sure. I mean, I'm not claiming we've solved what's well known to be a very, very hard problem. I think we could very easily use standard layout techniques at quite a high level to reorder boxes to try and make the use of silicon more optimal. I don't pretend to claim to know how to do that.
But the current complexity model, the cost model you have, does that account for?
Yeah, I think that actually would help a great deal, because the cost model lets you, as it were, hotspot your programs and see where you're unnecessarily doing lightweight stuff, where it would be better to maybe incorporate into something a bit more heavyweight. And similarly, where there are things that are independent, where you might want to pull boxes apart. The Hume box calculus lets you pull boxes apart horizontally as well as vertically, so you could potentially increase parallelism that way as well.
Last question. So when you say horizontally and vertical, that sounds very much related to Lava and the early Ruby. Is so that you have it's not just combinatorial structure. You have like a 2 or 3 dimensional structure in the composition of the boxes.
Yes, you can do that. Using the hierarchical model, you can certainly accomplish a multi-dimensional model. Yeah. But again, we have got all the pieces fitted together. I'm showing you one piece. Lava through Ruby is a much longer, much more refined and substantial pedigree than stuff I'm talking about. Okay? I think we've got like 15, 20 years to go to catch up on it.
These days, FPGAs have lots of extra stuff on them, as you indicated earlier on, like 1,000 18 by 18 multipliers or
Sure.
little cores or stuff like that. Have you got good ideas for how to make good use of those?
Not a clue.
I just started a project to try to figure it out.
So I did do some work in the past, which was trying to do really, really fast functional language interpreter, like cramming stuff into floating point registers. It's some appalling ancient history. It was on a PDP-11. Yeah. Trying to cram whole list nodes into a single floating point register, so that it didn't have to have multiple fetch execute cycles to transmit each list node. And it went really, really fast. It involved knowing sort of awful magic about what was going on in the floating point medium. I'm sorry, I'm just making this up as I go. I'm sure you know that. I've no idea.
Well, let's thank the big speaker again.